In this video, we'll cover the basics of automotive suspensions, which of course play an important role for the dynamic performance of a vehicle. Before we dive into the technical details, let's turn to the question, what are the main functions of an automotive suspension system? The first one is to enhance the ride quality by isolating the vehicle chassis from the vertical accelerations caused by the roughness of the road. A second function is to keep a steady contact between the tire and the road with a proper vertical tire force in order to maintain the maneuverability of the car. As we have seen in earlier videos, the vertical tire force is needed in order to get a lateral and longitudinal tire force. In other words, if the vertical tire force becomes too small, there can be no proper steering or acceleration and braking of the car. A third function is to optimize the handling performance of the vehicle in different dynamic situations. Handling performance meaning properties such as understeer and oversteer, limits of handling, and so on. The basic idea is that these properties are not static, but they are dynamic, meaning that they change with the driving conditions such as the roll angle or the pitch angle of the vehicle. A fourth function is to minimize the wear of the tires and parts of the suspension and the chassis due to dynamic loads acting on the car. Additional factors that affect the choice and design of suspension systems are cost, weight, dimensions, robustness, and ease of assembly. In the rest of this video, we'll look at different design choices for automotive suspension systems. The question of how these different design choices will then affect the handling performance of the vehicle in different dynamic situations will then be the subject of the subsequent videos. Automotive suspensions can be characterized by falling into one of two groups. First, solid axle suspensions, and second, independent suspensions. Solid axle suspensions are such that the wheels are mounted to a rigid beam, which represents the axle itself and links the wheels together in the sense that they cannot move independently of each other. So, as illustrated by the two pictures at the bottom, if one of the wheels of a solid axle drives over a bump in the road, this will be compensated for by the entire solid axle. Hence, also the wheel on the other side of the axle is affected by this bump. A solid axle may either be powered, in which case it's also referred to as a live axle, or it may be unpowered, in which case it's also referred to as a dead axle. The main advantages of solid axles are their simple design, that they are inexpensive to manufacture, and they're very robust. Today, solid axle suspensions are still used for some production cars, but much less frequently than they used to be. They are, however, commonly found in trucks, trailers, and off-road vehicles. For independent suspensions, the axle itself is more like an imaginary axle. In fact, they allow each wheel of the imaginary axle to move up and down independently. The advantages of independent suspensions are mostly based on the more flexible design options due to the more complex elastokinematic effects that we will discuss in more detail shortly. This generally results in better ride comfort and better tire road traction. Moreover, independent suspensions generally have a lower space requirement as compared to solid axle suspensions. Today, independent suspensions are used for the front axle of almost all production cars and for the rear axle of most production cars. Next, we'll look at some specific examples of solid axle suspensions and independent suspensions that are frequently used. The simplest way of attaching a solid axle to the vehicle chassis is to use a leaf spring suspension. The leaf spring suspension is a heritage from horse-drawn carriages, and it was very frequently used in early automobiles. For the leaf spring suspension, the solid axle, shown in green here, is attached to the vehicle frame, which is the basis of the vehicle chassis, by using semi-elliptic leaf springs that are shown in blue here. The leaf springs also provide a damping element due to the friction between the leaves. The leaf spring suspension was very common in automobiles until the late 1970s. Today, it is mostly used on trucks, trailers, and railway carriages. Leaf spring suspensions have several drawbacks. The main one is that they leave little control over important design parameters of a suspension, such as the damping ratio, or more importantly, the geometry of deformation of the suspension under different loads. This is also referred to as elastokinematics of the suspension. This fact is illustrated by the two figures on the left-hand side. In the upper one, the solid axle is used for acceleration of the vehicle, and in the lower one, the solid axle is used for braking of the vehicle. In both cases, of course, there will be a deformation of the leaf spring into a shape that's similar to an S. However, as you can see, there's very little control over how exactly the leaf spring will deform, and hence over the elastokinematics of the suspension. A common construction form that's also of great historical importance is the combination of a live axle with leaf spring suspensions in the form of a Hotchkiss drive, as shown in the figure on the right-hand side. In the Hotchkiss drive, the differential, shown in red, is integrated into the solid axle, with the drive shaft coming from the engine at the front of the vehicle. The Hotchkiss drive was a very common layout for front-engine, rear-wheel drive cars until the 1970s. It is still used today for many light and heavy trucks and some SUVs. With respect to automotive history, solid axle suspensions have evolved from leaf spring suspensions to so-called multilink suspensions. These are based on so-called links or arms, which are nothing but solid bars that are used to control the kinematics of a suspension. They can also be used with a leaf spring suspension in order to enhance its dynamics. For example, using a trailing arm, as shown in the figure on the right-hand side, which is also called an anti-tramp bar in the context of a leaf spring suspension. And what the anti-tramp bar does, it constrains the way the solid axle can move, in the sense that it only allows for the solid axle to move up and down at the end of the tramp bar, and not in particular longitudinally along the vehicle. Similarly, a triangular linkage, as shown in the image on the right-hand side, can be used to control the lateral motion of the solid axle. As a result, the solid axle can still move up and down, but the triangular linkage restricts the lateral motion of the axis, which is important, for instance, in turning maneuvers of the car. What all of these links or arms essentially do is restrict the degrees of freedom of the relative motion between the solid axle and the chassis of the vehicle, or at least they make them very stiff. However, they have to be designed such that at least 2 degrees of freedom are still permitted. First, a translatory motion in the vertical direction, and second, a rotatory motion around the longitudinal axis. In fact, there are many different numbers and designs of these links or arms, so it's impossible to cover all of them. An important example is the 4-link suspension that's shown in the figure on the right-hand side. Here, the drive shaft and differential, shown in red, are rigidly connected with the solid axle, shown in green. The solid axle is connected to the vehicle frame, shown in white, by the use of a total of 4 links, 2 lower links, shown in purple, and 2 upper links, shown in orange. By and large, one can say that the lower links are used to restrict the longitudinal motion of the solid axle, and the upper links are used to restrict the lateral motion of the solid axle. That's because the upper links are installed at a larger angle to the longitudinal axis of the vehicle compared with the lower links. Of course, that's not the entire truth, because also the upper links will absorb some of the longitudinal forces and the lower links will absorb some of the lateral forces. In a sense, the 2 upper links are kind of equivalent to the triangular linkage that was shown on the previous page. And that's why there also exists a 3-link suspension where the 2 upper links are replaced with this triangular linkage. Since the kinematics of this suspension are much more well defined due to the 4 links, the leaf spring can here be replaced by a coil spring and a linear damper. Now let's turn our attention to the class of independent suspensions. The 2 most common types by far are the double wishbone suspension and the McPherson strut. The first one, the double wishbone suspension, is sometimes also called the double A-arm suspension or the short long arm suspension. The name double wishbone suspension or double A-arm suspension pretty much explains itself when we look at an image. Namely, the suspension is made up of 2 control arms, which for their shape are called the upper wishbone and the lower wishbone, or the upper and lower A-arm respectively. Each of the control arms is attached to the vehicle chassis in 2 points, allowing them a rotational degree of freedom around these axes relative to the vehicle chassis. Since the double wishbone suspension is an independent suspension, it only carries a single wheel instead of an entire solid axle. This single wheel is mounted in this white part here that is called the wheel carrier or the steering knuckle, depending on whether the suspension is for a steered axle or a non-steered axle. The 2 arms may have different lengths, and sometimes these arms are replaced with just another link, but the functionality of the resulting suspension is very similar. The coil spring and the damper are loosely attached to the lower arm, but they can also be found arranged in a different way in other types of double wishbone suspensions than the one drawn here. So the common characteristic of the double wishbone suspension is really the combination of an upper and a lower control arm, which are fixed to the vehicle chassis in this way. A big advantage of the double wishbone suspension system is that it offers many independent design parameters, for example, to adjust the alignment of the wheels during turns. It is quite common in production vehicles, and it's also frequently used for race cars. So for example, if you look at the front suspensions of a Formula One car, you will recognize the double wishbone suspension system. The only main drawback of this suspension is that it is rather complex and expensive to manufacture. And that's why for many production cars, the preferred type of independent suspension is the McPherson strut. Looking at a functional diagram of the McPherson strut, the lower part of this suspension is actually quite similar to the double wishbone suspension, namely consisting of a control arm or other types of links that are attached to the vehicle chassis. The main difference is that the strut, which contains the damper and the coil spring, is rigidly attached to the wheel carrier or steering knuckle. In contrast, for the double wishbone suspension, the connection between the spring damper element and the lower wishbone is actually a flexible connection. The McPherson strut is less costly, less complex to manufacture, and lighter than the double wishbone suspension. It is therefore very common in front drive production vehicles.